So, good day, MatE 21 class. So, hopefully you are self-quarantining at home and practicing proper social distancing. So, medyo hindi yung kinakausap ng mga kapamilya dyan. But anyways, I'll bring back some of our lectures para if bored kayo, pag may papakinggan naman kayo or may makita kayo. So, now let's uh, go back to our imperfections in solids. So, this was our previous lecture that I'm just transcribing into a recording because of, well, continuity. So first, we must remember there is no such thing as a perfect crystal. All crystals have, well, defects. So these defects are imperfections in the crystallinity or the regular geometrical arrangement of the atoms in a crystalline solid. This can be either 0 dimension, 1 dimension, 2 dimension, or 3 dimension, and these are represented by point, line, planar, and volume or bulk defects for the 0, 1, 2, and 3 dimensions respectively. So first, let's look at what we call our point defects. So point defects are defects in which one atom is either missing or iba yung nakalagay dun sa lattice site na atom na yun. So for metals, there are three different kinds of point defects. You have your vacancies, self-interstitials, and your impurity atoms. So for your vacancies, a vacancy is when a lattice site is missing the atom that is supposed to be there. So in this case, what is shown in the slide is what we call your vacancy. Nakita natin dun sa gitna, ito, walang atom dyan. And pag nangyari yan is nagkakaroon tayo ng distortion in the lattice plane of the crystal. Since magkakaroon ng space yung nearby atoms dun sa vacancy natin na para mag-move, i-fill up nyo ng konti yung space na yun, which would cause stresses in the vicinity of that vacancy. So this would misalign some of our atoms near that vacancy. So in our TEM, or transmission electron microscopy, we can actually see our vacancies in our atoms. Vacancies are always present in our atoms. It is never not present except for the theoretical 0 Kelvin, which we will never reach. As you can see here, this is a vacancy here. Meron tayong vacancy dito. Meron tayong vacancy dito. And so on. So a formula for vacancy is given by the formula shown in the slide. NV is equal to N exponential of negative QV over KT, where NV is the total number of vacancies. So NV is the total number of vacancies. N is the total number of atomic sites. E is your exponential. So E is, remember, your Euler's number. QV is the energy of formation of the vacancy. T is the absolute temperature in Kelvin, and K is the Boltzmann constant. The Boltzmann constant can be expressed as 8.62 times 10 to the negative 5 electron volts per atom Kelvin, or 1.38 times 10 to the negative 23 joules per atom Kelvin. You also know this Boltzmann constant in chemistry. This is your gas constant. Yung gas constant nyo, yun lang yung Boltzmann constant, but it is now expressed per mole rather than per atom. Kaya nakita nyo meron siyang 8.31 joules per mole Kelvin. This is your gas constant. Hirap magsulat ng touchpad. Constant. So from this formula, we can see that your vacancy, number of vacancies, increase with temperature. Since exponential of negative 1 over T is just exponential T. Mangyari dyan is habang tumataas in temperature, we'll expect that the number of vacancies in your crystal would increase. The presence of these vacancies is essential since in solid state processes like say doping or carburization nitridation, the number of vacancies dictate the rate in which our processes can occur in. So as an example, we take this problem. So we have already solved this in class. You can calculate the equilibrium number of vacancies per cubic meter for copper at 1000 degrees Celsius using our formula before. The energy for vacancy formation is 0.9 electron volt per atom. The atomic weight and density at 1000 degrees Celsius for copper are 63.5 grams per mole and 8.4 grams per cm cubed, respectively. So in this case, we have your activation energy. This is your activation energy, 0.9 electron volts per atom. And we also have the temperature, 1000 degrees Celsius or 1273 Kelvin. We also have the Boltzmann constant. We can now look, so to calculate for our, to calculate for the number of vacancies per cubic meter, we can now use our formula. Dun sa formula natin, ang nawawala lang is yung N, or the number of lattice sites. But as we have seen before, we can calculate for the number of lattice sites from the density and from the molar mass. 63.5 grams per mole, 8.4 grams per cm cube. We can get an idea on the number of atoms or the number of lattice sites per volume, and we can plug that into our formula and we get the equilibrium number of vacancies per cubic meter at 1000 degrees Celsius for our copper metal. So that problem is actually found in your canister, sample problem in canister, and this is the solution for that one. So to get N, or the number of lattice sites, we can just use your density and your atomic weight. To get 8.0 times 10 to the 28 atoms per meter cube, that's the number of lattice sites per meter cube. We can use that back into our equation here, and we can get that there will be 2.2 times 10 to the 25 vacancies per meter cube for our copper crystal at 1000 degrees Celsius or 1273 Kelvin. So now let's look at another type of point defect in metals. We have your self-interstitial. Self-interstitial is when your atom, your host atom, rather than going to its due to its proper lattice position, it goes to an interstitial site. So an atom from the crystal is positioned in an interstitial site, and this would cause a distortion on the arrangement of your crystal since mas maliit na hamak yung interstitial site natin than your atom. So that would cause strain in the nearby vicinity, which will cause distortion in your crystal. In metals, this does not generally happen in large quantities since this is not very unfavorable due to the size constraints of those interstitial sites. Lastly, we have your impurity atoms. So atoms are incorporated into your crystal that are not the same as your host atom. So most of the time, these atoms are intentionally added to improve the properties of your material. So most of the metals that we use in industry is actually impure. Actually, halos, hindi, lahat sila. So even yung mga pure na copper natin or iron or let's say titanium or aluminum, may mga halo yan. Kasi napakahirap mag-purify ng metal such that matatanggal mo lahat ng impurity atoms mo. So shown in the right, shown in the left is different forms of copper. So you have copper, you have brass. Brass is an alloy of copper, which we add zinc, and we also have bronze. Pag bronze naman, we add tin. So copper, pure copper we usually use in electrical applications. Meanwhile, yung brass and bronze natin, ginagamit natin yan more for pipe fittings and other structural implements. So examples of our impurity atoms, so we have copper and nickel, bronze and brass. Again, bronze is copper plus tin and brass is copper plus zinc. You also have your interstitial impurities, carbon in iron and nitrogen in iron. So the difference between your substitutional and interstitial impurities is where they tend to go in our lattice. Pag interstitial impurity mo, it will tend to go inside an interstitial site of your crystal. Meanwhile, for a substitutional impurity, this will tend to replace the host atom in its lattice position. So in metals, we have what we call your solid solutions, or ito yung more generally known as your alloys. So solid solutions is when your crystal structure is maintained when adding solute atoms to the host material. Think of it as salt water. Salt is one phase, water is another phase. If you combine salt and water below the solubility limit, makakuha tayo ng salt water which is just one phase, liquid phase. So same lang dito, yung phase ng ating mixture of two metals will be just one phase or one crystal structure lang ang meron tayo. So there are two different types. You have your substitutional and interstitial solid solutions. So for substitutional solid solutions, we have the Hume rotary rules to dictate whether or not we can create a substitutional solid solution. So first, we have your atomic size factor. The radii difference between two different atoms, the host atom lattice, and the impurity should be less than 15%. The electronegativity difference between the two should be small. Their crystal structure should be somewhat similar. So, mas maganda yung probability na maging solid solution sila if their crystal structure are the same. And the valences, or the valence electrons of the impurity should be higher or at least the same as yung ating solvent metal or yung ating host lattice. So let's take an example, the gold alloys. Gold alloys is basically yung jewelry natin, never natin yan nakikita as pure gold. Because pure gold is soft. Due to this softness, this ductility, pag ginamit natin siya as in its pure form, mayuyupi agad yung mga jewelry natin. Ayaw natin mangyari yun. So the carat system is divided into 24 parts. So pag 24 carat yung gold mo, you have pure gold. If 21 carat siya, that's 21 parts gold and 3 parts, let's say silver or copper or any other additional or impurity metal. So for our interstitial impurities, they usually go depending on the metal or the crystal structure on the tetrahedral or octahedral sites. So our impurity atoms usually tend to go in the spaces in which kasya sila. So depende sa crystal structure, merong mas malaki. So for FCC and BCC, it's in your prob set, which one of these are bigger. But for each of these, makita natin yung octahedral and tetrahedral sites nila. So for the FCC structure, the octahedral site is along the edge, in the midpoint of the edge of the cube, while the tetrahedral, or in the center of the cube, while the tetrahedral site is at 1/4, 1/4, 1/4 position for FCC. For BCC, your octahedral position is placed at the edge of the cube. So you have one body center. Meron kang pangalawang body center dito. Pangatlo, pang-apat, and 5, 6 octahedral. Well, the tetrahedral site is here. Dito siya. It's at 1, 1/2, 1/4, or for me, mas madali siya, 0, 1/2, 1/4. And it is connected to your two edge atoms here and another body center atom dito. So one of the most important interstitial impurity metals, or metals that exhibit interstitial impurities that we have, is steel. Steel is the backbone of modern skyscraper, modern infrastructure, because it's relatively easy to create and it's relatively abundant. So steel is just carbon and iron. So the max concentration of carbon in your iron depends on the crystal structure. In FCC, it's 2%, and in BCC, it's just 0.025%. This has something to do with how big the interstitial sites in FCC and BCC are. Now let's look at point defects in our ceramics. So for point defects in our ceramics, we have three different types. We have your stoichiometric. So you have your Schottky, Frenkel, and andesite defects. You have your non-stoichiometric defects and your impurity atoms. So first, for stoichiometric defects, the cation to anion ratio does not change, or we say the crystal chemistry or the crystal stoichiometry is maintained. There are three different types of stoichiometric defects. You have your Schottky, Frenkel, and anti-site defects. So first, let's look at the first two, Schottky and Frenkel. So Schottky defects is created when one pair, or at least one pair, or one formula unit of your ceramic is removed from the lattice. So this is created by removing a cation and anion pair from the interior of the crystal. Meanwhile, for a Frenkel defect, this happens when either the cation or the anion moves from its normal lattice position into an interstitial site. So for most ceramics, the more common Frenkel defect is the cation Frenkel defect, since usually yung cations natin is mas maliit than your anions. And we have also anti-site defects. Anti-site defects happens in covalent ceramics usually, or in your complex ceramics, since this involves the movement of one atom to another lattice site that hindi niya talaga pag-aari. Or basically, nagsaswap yung dalawang atoms natin ng lattice position. So this happens in your covalent ceramics and complex oxides, since mas madali sila mag-interchange ng position, mas less yung electrostatic repulsion between those two atoms. So shown here is silicon carbide, and we can see that yung silicon natin dito, it's in your carbon position, and your carbon is in your silicon position. So dapat magkabaliktad talaga sila. So we also have what we call your non-stoichiometric defects in our ceramics. Non-stoichiometric defects means that there will be a deviation from the formula unit ratio or the crystal chemistry of your structure. So this may occur for ceramics which has more than one valence states for their cations or maybe your anions. So an example is iron oxide. We know that Fe has different oxidation states. We have Fe2O3, Fe3O4, and FeO. That's plus 2 and plus 3 na Fe. And in this case, FeO can be represented as Fe1 minus XO. Lastly, we can also have impurities in our ceramics. Again, no material is 100% pure. Usually, meron talaga tayong impurities in our structures. So for impurities in ceramics, the considerations, depending on whether saan pupunta yung impurities natin, is their charge and their size. So if they are substitutional impurities, for example, they will tend to go in the position in which the size and charge are the same as the host lattice. So let's say here, meron tayong NaCl na lattice. Let's say this is NaCl. So meron tayong Br minus na impurity. This Br minus impurity, considering the size and the charge of the Br ion, this will tend to go into your Cl lattice site, because Cl and Br has same charges, negative 1 sila pareho, and Cl and Br has relatively the same size. Kumpara mo yung Na na mas maliit siya than, let's say, Br. So usually in the incorporation of impurities in the ceramics, if we have alluvalent defects, so alluvalent is when your defects are not the same charge as your host lattice, further defects may be formed in our lattice to accommodate the incorporation of our impurity. So now let's go to our line defects. So line defects are characterized in crystals by what we call our dislocations. Dislocations is a linear defect around which some of our atoms are misaligned. So makita natin yan in your crystal, parang meron kang line in which hindi na nagko-continue yung crystallinity ng ating structure. So this may be classified as your edge, screw, or a combination of the both, which we call the mixed dislocation. So for an edge dislocation, this occurs when an extra half plane of atoms, extra half plane here, is incorporated inside your crystal. Parang meron kang wedge na nandito. Magkakaroon tayo ng dislocation here, papasok to that crystal. So the Berger's vector, this is just a vector that we denote to quantify the magnitude and direction of the lattice distortion associated with this dislocation. So in this case, makita natin, ito yung dislocation line mo. Dito sa baba, you have high tension, and dito, nako-compress yung ating atoms. Kaya yung notation natin for this line here is ganito. So dito sa baba, stretch siya. Sa taas, na-compress siya. So in this case, we have edge dislocations dito. And here. So dito, naghiwalay yung dalawang atoms, meron kang tension, and dito na-compress siya sa taas. You have compression. Meanwhile, yung screw dislocation natin, it is as if you're shearing a half plane of our crystal. So parang twist mo siya to get this feature here. Makita natin the dislocation line would be paganto. So it is as if umikot siya along that dislocation line. And lastly, we have your mixed dislocation. It's a combination of your edge and screw dislocation. So you have here your edge. This is edge. And dito, you have screw. So in this case, yung Berger's vector natin, mag-morph siya to accommodate both edge and screw dislocations. So sources of dislocations for in crystals are usually when we crystallize our crystal from a liquid melt. So yung crystallization natin, and from working our metal, or when we apply stress or strain, we're straining our metal. So doon nanggagaling yung dislocations into our crystals. So in metalworking or in common use, usually mas gusto natin na maraming dislocation actually yung mga bakal natin, because we have a concept which we call strain hardening, which you would learn in MatE 22, in which pag mas mataas yung strain natin, tumataas yung number of dislocations. Pag tumaas yung working natin dun sa bakal natin, tataas yung number of dislocations. And this will actually increase the strength of our materials, which is frankly really amazing. So I'll end here for now. So now we move on to our planar defects, or our two-dimensional defects. But before that, some words from our sponsor, Sleepasil. Nahihirapan ka ba matulog dahil sa anxiety na dala ng COVID-19 na pandemic? Well, ako, nahihirapan ako. Kaya mga 1 linggo rin ako hindi nag-upload ng lectures. Masyado akong kinabahan sa mga nangyayari sa ating hinaharap at sa kapaligiran natin, hanggang pinayuhan ako ng ate ko na gumamit ng Sleepasil. Sleepasil is a formulation na may kasama melatonin, chamomile, and valerian. Nakaka-relax siya at isa siyang multivitamin, sumataas ang inyong immunity at pinapatulog ka sa gabi. Para sa mga taong nag-suffer ng anxiety, katulad ko, ng mga nakarang araw na ito, rin-recommend ako na gumamit kayo ng Sleepasil. Ito ay mabibili natin sa ating mga malalapit na drugstore na sana bukas pa: Mercury Drug, Watson, Southstar Drug, Rose Pharmacy, and Generica Drugstore. So ayun, gamitin nyo ang Sleepasil. Amin lang po pinapaalala, ang Sleepasil ay hindi gamot at hindi dapat ituring gamot sa anumang uri ng sakit. So now, let's go to our planar defects. So one, we have your external surfaces. So for external surfaces, these are the continuities of your crystal, discontinuities in our crystal due to the termination of the crystal pattern. Or basically, ito yung outer faces ng ating mga bagay-bagay. So these are your external surfaces. So atoms at the surface, they lack the required coordination number that is expected for your crystal, they have a higher energy state than the atoms at interior positions, kaya meron tayong tinatawag na surface energy. We also have what we call your grain boundaries. So grains are regions of crystals na pare-pareho yung alignment ng ating crystal. So, grain boundaries are those sites in which yung pare-pareho ng alignment na crystal ay nag-meet. So, these are sites where our mismatched crystals meet. And yung grain boundaries natin, yung boundaries na to is yung boundary between two like or dislike faces. So, ang grain boundaries natin, though usually ginagamit natin ng grain boundary na term for two like crystals na magkaiba lang yung kanilang orientation, pero same yung composition nila. So we have different kinds of grain boundaries. We have your high angle and low angle grain boundaries, depende din sa angle ng attack or the angle ng mismatch ng ating two different crystal regions. But you would learn about these types of boundaries in higher MatE. So for now, tandaan nyo lang for yung crystalline regions natin, pag isang alignment lang sila, isang green lang yun. Tapos, pag nag-meet yung dalawang crystals mo na magkaiba yung alignment, magkakaroon ka ng grain boundary. So we also have what we call our twin boundaries. So twin boundaries, like your grain boundaries, meron kang discontinuity in the alignment of our crystal. But in this case, meron tayong, instead of a grain boundary, we have a twin boundary. So tinawag natin siyang twin boundary because nag-act as if mirror yung ating boundary. So in this case, yung twin boundary mo is ito. And makita natin dito, that it's as if we're mirroring this region here. So lastly, for our planar defects, we have your stacking faults. So stacking faults are when there's an interruption or hindi nasusunod yung preferred na stacking ng ating structure. So remember that for closed-packed structures, we have two different kinds of stacking. We have your AB, AB, AB stacking for HCP kind of structures and your ABC, ABC, ABC for, well, yung mga nagko-form ng FCC. But sometimes, nagiging ABC, AB, 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 ABC, or ABC, 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 AB siya. Nagkakaroon ka ng fault in the stacking which would cause defects in our crystal. Next, we go to our volume defects. So volume defects are defects in which isang malaking region na ng crystal or isang bulk region ng crystal mo ang nawala. So a classic example of your volume defects are our pores and our voids. So these are basically air pockets inside our crystal or basically walang material na malaking region doon. So our pores and voids can range from microns in size in diameter to about millimeters in size. We also have your cracks. So alam niyo naman kung ano yung crack. So it can be surface or internal cracks. Next, we have your foreign inclusions. So this is kind of an impurity but in a macro scale. So mas malaki, parang meron kang bulk na impurity or bulk na foreign object na nakalagay sa ating material. And we also have notches. So notches are kind of like cracks, but usually nalagay natin to intentionally for some testing. So parang meron kang indentation in your material. Next, we look at our polymer defects. So for polymer defects, since highly entropic ang structure ng polymer, so by highly entropic, medyo mahirap sila i-crystallize, dun sa innate na hardness or innate na pagkahirap na mag-crystallize ng ating polymers, nakita natin na marami kang defects na magagawa. So we can actually consider an amorphous region in a crystalline polymer as a defect. And we can see different kinds of defects in our polymers. So meron tayong boundary nung crystallite natin. So this is akin to like a grain boundary. Meron din tayong screw dislocation and edge dislocation dito. So meron din dislocations dito. You have also vacancies. You have the meeting of the chain ends. So parang meron kang discontinuity in the chain. You have the inclusion of impurities in your crystal. You have amorphous regions. You have chains that are not inside your crystallite. And you have branches and so on. So marami tayong pwedeng polymer defects in, well, our polymers. So now let's talk about microstructure. So your microstructure, this is the structure of a material when we look at it under a microscope. So usually above 25x or 25 times the resolution or ang tawag dito, yung zoom nung mata ng tao, yung kino-consider nating microstructure. So from the microstructure, we can see whether or not our material is monocrystalline or polycrystalline, or sometimes makita natin, hindi siya crystalline. So for a monocrystalline material, the orientation of your crystal is the same all throughout your structure. So wala tayong grains dito, ay wala tayong masyadong grains or wala tayong grains for the system since isa lang naman yung orientation ng crystal mo. Wala tayong grains, wala tayong grain boundaries. So an example of this, yung nasa kanan, this one, this is actually your silicon crystal. This is silicon single crystal which we use for the formation of our IC devices. Itong nasa kaliwa, ganito usually ang microstructure natin or yung structure. So usually for engine parts, since tumataas yung temperature nila to protect against creep, we want large grains. So mas monocrystalline, mas better for those kinds of parts. Next, we have your polycrystalline. So for polycrystalline, it's made up of a number of smaller crystals. These has what we call your grains in them. So yeah, meron tayong grains. And makita natin meron silang mga grain boundaries. So inherent yan usually in our materials. Most of our materials without further processing happens to be polycrystalline. So the feature of a polycrystalline material is what we call your grain. The grain is when a part of the crystal region is fully aligned. Parang aligned sila, continuous and unbroken inside the area. And the regions in which your grains meet is what we call your grain boundaries. So yan. So these are your grain boundaries. These are sites at which our mismatched crystals or our grains meet. So in reality, yung grain boundaries natin, plain yan. Dito sa picture, mukha siyang line kasi tinitingnan lang natin yung edge ng surface. Pero pag tinignan natin yan in your metal, ang nangyayari talaga is your grains are actually three-dimensional while yung ating grain boundaries is parang yung surface area ng grains mo or yung surface ng area ng grains mo. So from the ASTM or yung standards natin for materials, we can determine the size of the grains by comparing it to a chart. So the grain size, n, small n, this one here, this can be computed by counting the number of grains inside a 1-inch square area of a 100 times micrograph. And using this formula, we can get yung small n natin or yung grain size number mo. For now, what you need to learn is just pag mas mataas yung grain number natin, if n is high, ibig sabihin, mas polycrystalline yung material. Mas maliit yung grains nila. If n is lower, let's say 1, the material would have larger grains. It would be less polycrystalline. So a modification to our ASTM grain size number when you're dealing with magnifications that are not at 100 times is the following formula. So you can just pause here or look at in the slides kung paano ginagamit itong formula na to. So this is basically just a conversion from the 100x na magnification to whatever magnification yung ginamit nyo in your testing. So there are other grain size determination techniques. You will learn about this in the future, hopefully, sa lab, ma-experience mo paano ginagamit. Meron tayo yung previous na method natin for ASTM na tinitingnan lang siya. We also have your planimetric and lineal methods in which tinitingnan natin yung area, yung planar and linear density ng grains natin for the different methods. So yan, this is an example of how you determine grains. So habang tumataas yung grain size number, nakita natin lumiliit yung ating grains. So yung grains natin, hindi lang lahat yan medyo bilog. Meron din siyang different shapes. Depende kung paano yung treatment na nangyari sa kanya. So pwede tayong magkaroon ng columnar grains. Meron tayo yung equiax grains. So medyo yan yung pabilog na. And meron tayong dendritic grains. So yung dendritic grains, or para siyang puno na nag-branch out from your branches. So para siyang dendrites, pine needles, parang ganyan yung shape niya. So yung dendrites natin, nakita natin yan, for example, in the plating of our copper. So here. So yung orientation ng grain natin, pwede natin siyang i-change by applying stress or shear stresses to our system. So for example, if we roll a metal which has equiax grains, ang may expect natin is that since re-roll natin yung bakal mo, mangyayari is parang mapipipi niya yung equiax grains natin na magiging mas elongated, mas columnar yung shape ng ating grains. So this may induce your crystal to have a preferred orientation, which would affect the properties of your crystal, which might make it from, let's say, an isotropic material to an anisotropic material, or magiging direction dependent na yung properties ng ating material. So another concept that you need to know when we're looking at the microstructure is the concept of phase. So a phase from your basic science, this is just yung homogeneous portion of a system that has uniform physical and chemical characteristics. So we know our basic phases, your solid, liquid, gas, plasma. So basically yan, so you have here, it's the liquid phase, yung water, and nasa kanan, it's a mixture of solid and liquid phases, your ice and your water. So for your materials, for your solids, pwede siya maging single phase or multi-phase material. Pag single phase, isang type of phase lang or isang type of crystal structure lang makita natin. So like dito na sa kaliwa, isang phase lang siya. Dito naman sa kabila, makita natin meron kang dalawang kulay, meron kang itim at nung puti. And upon further knowledge, so as you learn more about materials engineering, you will actually learn that this different colors, this actually represents the two different phases in our steel. So yung itim natin, that is your, if I'm correct, this is cementite, and yung medyo lighter regions natin is your ferrite. So in steel, usually ganito yung naging structure natin, nakita natin na multi-phase nga yung ating steel. So knowledge of these phases, or the amount, the composition, this can be obtained from what we call our phase diagrams. So sa phase diagrams natin, makakuha natin yung iba't ibang information na kailangan natin or pwede natin makuha for our material, like the phase amounts. So we can quantify how much of the phase is present for a specific concentration of our impurity, for example. So let's say you have 0.1% of carbon in steel. So ano yung magiging composition ni ferrite and cementite phase doon? We can also look at your phases by we can also qualitatively observe yung different shapes ng phases natin. So different phases in a certain material would tend to crystallize in different shapes or tend to align in different shapes. For example, austenite, martensite, and cementite. So these are different features that we can observe in our steel microstructure. We can also look at the sizes of our phases. So in steel, you have what we call pearlite. Pearlite is a mixture of a ferrite and cementite in a striated arrangement. So para siyang naka-bands. So we have what we call coarse and fine perlite, depende kung gaano kalaki yung spacing between your austenite and ferrite faces. And lastly, we have your phase distribution. So paano dinistribute yung ating faces from one another. So paano ka-disperse, gaano sila kumpol, and so on. So with that, we end our lecture 8 about the imperfections in our monolithic materials. So if you have any questions, just feel free to contact me either through email, through my cell phone, through the comment section. So please like and subscribe sa channel ko if ever magkakaroon man ako ng channel. Since pag hindi na tayo makabalik sa UP, parang mas gusto ko rin maging virtual YouTuber or YouTube star. Parang ganun. So with that, so hope you are all doing well, and I don't know. So this ends my lecture. Thank you.